So there's a small question. So in our this one equal to this one. So because x1 x2 is inner product, right? Okay. So lambda 1 equal to so this part is not zero. This part is greater or equal to 0 according to the inner product issue. So if this one is non-zero, so the only possibility is lambda 2 and lambda 1 will, so lambda 1 conjugate equal to lambda 2. Okay, but we just say lambda 1 and lambda 2 are different, right? I mean, here there's a small problem because we have conjugate. But the Hermitian matrix, okay, its eigenvalues are all real. Okay, for Hermitian matrix, the eigenvalues are all real. Did I talk about this? I think so, right? Eigenvalues are all real. Okay. Yeah, so well actually we prove this. So because eigenvalues are real, so lambda 1 and lambda 2, I mean you don't need to write a conjugate, because the conjugate for real number conjugate is the same to itself. So and we already know lambda 1 is different from lambda 2 at the beginning. So I mean what do we do? So this one and this one, the only possibility for these two to be the same is that the inner product, or like the h1, x1, x2 is 0. Okay, yeah, I think I could prove that. So if we have a distinct eigenvectors, in other words, we have n we have like n corresponding eigenvectors that are orthogonal to each other. So we have like a x1 equal to lambda 1 x1, a x2 equal to lambda 2 x2, a xn equal to lambda n xn, where lambda 1 to lambda n, they are all different, and by the way, they are all real, right? And also we know that x1, x2 up to xn, they are orthogonal to each other, right? Based on what we know. Then, okay, what we can do is that we can write it like this. We just use this vector. Well, actually, we can actually do a little bit better because, like, we know, like, eigenvector, we can make those eigenvector unit, right? Just divide each of them by its length, right? Then these eigenvectors are not only orthogonal but also normal, so they are also normal. So it will be, you know, lambda 1, x1, lambda 2, x2, lambda n, xn, right? So this is like an abbreviation of this set of equations, which is writing in a matrix form, right? 这个乘上第一个 column matrix，column vector 等于第一个 column vector， 乘上第二个 column vector 等于第二个 column vector。这样，这一直把这个刚刚那个整个写这样子。And then this will be decompose this one into this one times like a diagonal matrix。你自己算算看哦，你这 diagonal matrix， 你这个乘到这个是第一 ，the first row is lambda 1 x1。The second row is lambda 2 x2 and so on. Right? So if we let this one to be u, we just wrote a u equal to right? Sorry, UD. We just wrote this, right? Where diagonal matrix is this one. This is our D. And then if you multiply on the left hand side for both the inverse of u, then we have u inverse a u equal to u inverse u d, which is d. So if the eigenvalue of Hermitian matrix A are distinct, there exists a unitary matrix U that diagonalizes A. Oh, by the way, I wrote U inverse, but actually, okay, remember, these vectors, they are orthogonal to each other, right? So, you know, you can write this H inverse as HH, U inverse as UH. They are the same. Because these column vectors, they are orthogonal. So you know, like U equal to I, right? So that's unitary matrix. And here we have an example. Okay, A is like this. Take a closer look. This A obviously is a complex matrix, and A has to be Hermitian, by the way. So you can see that the diagonal is diagonal elements are real, and the you know, symmetric pairs are conjugate to each other. Okay, so P of A, PA of lambda equal to this one, so you can easily calculate it's like a lambda times lambda minus 3. So you have two eigenvalue, and with these two eigenvalues you can calculate like their corresponding eigenvector. When lambda y is 3, then xy is like that. Lambda 2 is 0, lambda 2, x2 is like that. By the way, we have to make this matrix U, the column vector has to be not only orthogonal, I mean, well, they are orthogonal because they have this different eigenvalue. We already know that. But we have to make them normal as well. So we have to divide their length. So U1 is like a 1 over square root of 3. This thing U2 is same thing, 1 over square root of 3. That. So U is because both have 1 over square root of 3. So you put 1 over square root of 3 outside. So you have the first column from here, and the second column from there. Okay? And the UHAU is going to be, the UH basically is the same thing. It's like the only difference is that it's a combination of a U. Okay, so the diagonal. Okay, you do a transpose and then do a conjugate. So this diagonal part becomes like this, and transpose. So this is like the inverse. So this is UH. Because this UH and U, they should be inverse to each other. So this one multiply this one, multiply this one. Okay, and we have a 1 over square root of 3. Okay, from UH and U. So multiply both to get this. So the result must be, the diagonal one. The diagonal like element. The first one is lambda 1. The second element is lambda 2. So 3, 0. Okay, you can verify this by yourself. Like basically like just what we did. Then it's a Schur's theorem. Okay, for each n by n matrix A, there exists a unitary matrix U such that UHAU is upper triangle. Okay, so this theorem is different from the previous one in the sense that this works for every n by n matrix A. Okay, any n by n matrix A. It doesn't have to be unitary. Sorry, it doesn't have to be Michel. It doesn't have to be Michel. So how do we prove that? What we want to show is that for any n by n matrix, okay, A, okay, so we can find like find a T, find a unitary matrix or any only matrix A, you can find okay, there exists a unitary matrix U, okay, which, you know, if you do UHAU, okay, it's going to be an upper triangular matrix, okay? So if you have that, obviously, okay, you multiply T, you multiply U on the left hand side, on both sides. You multiply UH on the right hand side on both sides, and you get this, right? Like A equal to UT UH. Okay, this is, we call this sure decomposition of A. And if A is a Hermitian, then matrix T will be diagonal. Okay, I mean, I already showed in previous slide that, you know, if A is Hermitian, you can find U to diagonalize A. Okay, there's no question about that. Okay, but how about like a general case? So this proof is by contradiction. Okay, by contradiction. So first, okay, when A is 1, the size of A is 1, then this is obviously correct, right? This is obviously correct. Because like you can just let U to be, well, number 1. Okay, I mean, single value 1. And you, you know, UHAU, well, 1 Hermitian, I mean, it's still 1. A and 1, I mean, obviously, I mean, it's still A, but since A only has 1 element, it must be upper triangular, right? Right? Because we have only 1 element. It's 1 by 1, right? Okay, so that's, you know, obviously the result is correct. So now, okay, let's assume, okay, this result is valid for K by K matrices. Okay, we want to show, okay, for K plus 1 by K plus 1 matrix, okay, we have that as well. Okay, so, okay, that you know, the eigenvalue and eigenvectors of A. Remember, this A is of size K plus 1 by K plus 1. So, so we have like you know, K plus 1 eigenvector, eigenvalues, and K plus 1 eigenvectors, and partly from like multiple roots. Okay， 就是说，可能有些让答 I 是重复的，基本上，we have like K plus 1 eigenvectors and you know, K plus 1 lambdas, and then okay, for this you know, W1, W2 to WK plus 1, okay. Because like this eigenvectors, we know like this eigenvector like span a space, so we can, you know, we can use Gram-Schmidt process to construct orthonormal basis. Okay. W1 to WK plus 1. Okay. So here, we don't care about this part. We don't care about this part. Okay? The only thing we care is the first the first column, first row element is not that one. Okay, because it's corresponding to W1. Okay? I mean, remember like Grant Smith, like a process, you just try to make like the first vector, unit vector, that's it, right? Okay, and then for the second vector, you need to get rid of the projection part, okay, to the first vector, and that whatever left over is, and then you normalize it, that's the second vector, and so on. So there are a lot of other things to do, but you know, like for the first vector, okay, there's really not much to do, like you just like normalize it, okay, because you just normalize it. So the orthonormal basis W1 to WK plus 1. I mean, if you multiply, by the way, because they are orthonormal, so the WHW